Every year, we lose lives, money, and time to disease outbreaks that could have been stopped if we only saw them coming. But what if we can see them coming? What if the key signals of disease emergence were already around us, in the air, the water, in the landscape, our urban environments, and these were visible from space? I work at the intersection of Earth observation, artificial intelligence, and public health. And I help decision makers, scientists, doctors, analysts, people like you, understand how to turn space-based data into early warning systems for disease monitoring and control. In this video, we're going to talk about why traditional outbreak models can fail and how Earth observation is fixing them. We'll go from the limits of case-based disease tracking to satellite-driven prediction systems that can spot outbreaks before the first case hits the clinic. And this isn't science fiction. This is operational science, and it's already saving lives. Let's start with our problem. We don't catch outbreaks early enough. Most disease prediction models are built on reported cases. Someone gets sick, goes to the clinic, the data gets recorded, analyzed, and eventually, hopefully, alerts get raised. But by that time, it's often too late. Outbreaks like malaria, dengue, or cholera can spread fast. Waiting for cases means we're always reacting and not preventing. And in many parts of the world, disease tracking systems are incomplete or underfunded. A village clinic may take weeks to report a spike, or may never report at all. In conflict zones, especially, or rural areas, entire outbreaks can go undocumented. There's also bias. Case reports reflect access to care. If people can't get to a clinic, their illness isn't counted. Another issue, most models ignore the environment. They focus on humans rather than the ecosystem that support disease. But diseases don't emerge in a vacuum. Moreover, most disease models assume that contributing factors, such as climate, human behavior, and infrastructure, built infrastructure, remain constant. But in reality, our world is dynamic and complex, with these variables shifting over time and space. Rainfall creates mosquito habitats. Algal blooms drive cholera. Urban heat, dust, and dry areas can trigger respiratory flare-ups. These signals often appear weeks before any cases. So why aren't we watching them comprehensively and tying them to disease prediction? Traditional health tracking is like predicting a flood by looking at insurance claims rather than rainfall. That's how we've been predicting disease. We need to move upstream to the root causes, and that's where space-based data comes in. Right now, hundreds of Earth observation satellites are orbiting the Earth. Actually, a lot more than that. They are capturing data on rainfall, temperature, vegetation, land use, and much more. They're essentially a planetary nervous system, watching every meter of the globe every day. And this is what we call Earth observation. More importantly, it's not just pretty pictures. These satellites measure rainfall totals and vegetation health, like through NDVI, which is basically a formula for measuring plant health from satellite data. Also, land surface temperature, flood and drought conditions, human activity through nighttime lights, and the health and amount of urban green space. These data are directly linked to disease risk. For example, heavy rains followed by hot days. This is a mosquito paradise. Flooded riverbanks and clogged drains are breeding grounds. Algal blooms, fueled by warming oceans and high nutrient runoff, create a hotspot for cholera-carrying plankton. And satellite sensors detect all of this in near real time. Also in urban areas, Earth observation shows heat islands, so places that trap heat and worsen respiratory conditions. In urban environments, heat is not consistent. It varies by the types of buildings, their materials, the amount of pavement, vegetation, and more. In forests, deforestation seen from space can signal a higher risk of disease jumping from animals to humans. Earth observation gives us global, continuous, and objective insight into drivers of disease before anyone shows symptoms. But seeing risk is only half the battle. The next step is combining Earth observation with AI models that can forecast what's likely to happen next. When you combine Earth observation with AI predictions, it's like switching from a rearview mirror to a forward-facing radar. So how does this work in practice? Let's take a simple example, malaria. To predict outbreaks, we pull in satellite-derived data, rainfall, vegetation cover, and temperature. We then add population density, where are the people, elevation, and even mobile phone-based mobility patterns if we have this. Machine learning models analyze this data to find patterns. Do outbreaks occur 2 weeks after heavy rain in the region? Are malaria spikes more likely when vegetation stays dense for 10 days? Is malaria more prevalent near water bodies? Once trained, the model can scan current conditions and flag areas at risk, sometimes weeks before clinical data would. During my time collaborating with the World Health Organization, we use this kind of model across the African continent. It accurately predicted malaria surges. So let's go beyond this and add on top of it. In another project, a past project, Health GeoJunction, while I was at Penn State, we layered environmental data with news signals, media. If media in a remote region is reporting strange illness, and we can see Earth observation showing heavy rain and high vegetation, then we can flag it for further review. And we can extract from these media reports co-occurring locations. This could signal future at-risk areas or past transmission networks. The key is data fusion. No single data set is enough, but together, Earth observation, historical data, human behavior, all paint a powerful picture. This is the new science of disease forecasting. It's not just about cases, it's about context, patterns, and seeing ahead. And this science is no longer experimental, it's operational. I want to take a quick pause here to emphasize that none of this works without collaboration. If you're a decision maker, a scientist, or doctor, working on tough public health or environmental problems, I'd love to help build solutions with you. Feel free to reach out anytime. Now, let's talk about impact. When done right, Earth observation-based disease prediction doesn't just sound good, it works. Take cholera in coastal Bangladesh. Scientists used satellite data to monitor sea surface temperatures and chlorophyll, a proxy for plankton blooms that host cholera bacteria. These models allowed them to forecast risk weeks before cases emerged. In Kenya, we see malaria prediction in action. Rainfall and vegetation data highlighted where mosquitoes were likely to breed. Health agencies use this information to pre-position bed nets and launch awareness campaigns before a single clinic visit. In Brazil, high-resolution satellite imagery helped identify swimming holes and rooftop water containers in urban areas. These are prime breeding grounds for dengue-carrying mosquitoes. These insights allowed laser-focused vector control, saving money and lives. In my work with the WHO, our Earth observation-driven models flagged high-risk areas in Africa based on near real-time environmental warning signs. And during our Health GeoJunction project at Penn State, we discovered the power of digital news. If a local newspaper reports a mystery fever, and it's during the rainy season, this can be aligned with rising vegetation and moisture levels from satellite feeds. Blue Dot, it's a Canadian company, used similar techniques to warn about COVID long before mainstream media connected the dots. These projects are not hypothetical. These are proven interventions made possible by space-based or global data fusion insights. And what's common across all of them? Time. The importance of time. These systems give decision makers more time to act and more time to save lives. We've talked a lot about satellites, but let's get to the engine behind it all, AI, artificial intelligence. Earth observation produces massive amounts of data, way more than humans can interpret manually. And that's where machine learning and AI come in. Algorithms can detect complex correlations, like linking rainfall patterns to disease spikes, or vegetation cycles to mosquito population booms. And when we combine Earth observation with human mobility data, road and building data, maps, access to clean water, or clinic reports, AI can spot subtle signals that would have otherwise been missed. However, it's critical to understand that AI isn't magic. We're not going to go and build like a simple machine learning model that solves disease spread. It needs smart people who can see the bigger picture. And of course, you hear this a lot, garbage data leads to garbage forecasts. So we must guide these models with domain knowledge. And that's why we don't just build and deploy models. We embed them in workflows with public health experts. They interpret the results, provide context, refine predictions, and dictate simulations. Done right, AI amplifies human expertise. It lets us focus attention where it's needed most and cut through the noise. A model is only as useful as its interface. So let's talk about tools. Let me tell you something I learned working with the WHO in Africa. I saw how critical it is to not just build models, but build systems. Systems that let officials zoom into regions, see color-coded risk maps, get alerts that tell responders, hey, this district has a high dengue probability next week. These tools need to be simple, visual, and actionable. The people making decisions aren't always modelers, analysts. They're health directors, local planners, and even field teams. In Health GeoJunction, we incorporated near real-time feeds that frontline responders could quickly scan for emerging risks. In addition, you may need mobile apps in rural areas, multilingual interfaces, and sometimes even offline tools that work without internet connection. The key is integration. Prediction systems must fit into existing health infrastructure. If it doesn't work for the people using it, it's not going to work at all. Building these types of platforms is where tech meets trust. So what does this all mean for you? And if you've made it this far, I can tell your brain is already connecting the dots. This isn't about satellites. It's about giving people time to act, time to prepare, time to save lives. If you're a public health official, consider how Earth observation could enhance your disease tracking systems. You don't need to become a satellite analyst, but understand the environmental signals driving disease risk helps you make earlier, better decisions. If you're in policy or funding, recognize this is a powerful frontier. Investing in Earth observation plus disease forecasting systems now can prevent massive costs later in outbreaks, loss of life, and emergency response. If you're a technologist or a researcher, this is a wide open space. There's room for innovation in modeling, visualization, communication, and integration. When I collaborated with the WHO, this is one thing we concluded. There is so much left to do. And for everyone else, you play a role too. Awareness matters. We often think of space as disconnected from Earth or looking outward. But Earth observation shows us that space is incredibly connected to how we live, how we suffer, and how we survive. I've spent my career building systems that blend science, satellites, and service. And I've seen firsthand how proper insight, delivered at the right time, can shift outcomes. We don't have to be reactive, we can be predictive. And we already have the tools. Thank you so much for joining me in this discussion of space-based disease prediction. We've covered why traditional models fail, how Earth observation fills the gaps, and the real-world systems making a difference. If you're working on projects in this space, or want to, you're not alone. This is a growing global community. I post videos that make cutting-edge science understandable, relevant, and usable, especially for people designing systems, building solutions, or shaping policy. In a future video, we'll dive into geospatial foundation models, something else that is making a big impact in public health. I'll talk about how they work, where they fall short, how we can fine-tune them for real-world impact, and how they're beginning to shape public health by powering large-scale mapping, outbreak forecasting, and infrastructure planning. If this sounds interesting, hit subscribe, leave a comment, or share this with somebody who should be thinking about satellite-based forecasting. And if you're a health leader, researcher, or funder ready to collaborate, I'd love to talk. Because this field isn't just about watching Earth. It's about protecting life on it. Environmental health is inevitably human health. And the more we can see, the more we can change. Thank you so much.